This is the solution video for exam 2, problem 5. And so basically this is a problem where I'm going to have 32K by 8 RAM chip is using coincident encoding by splitting the internal code into row and column select. So it's two-dimensional. This RAM chip applies only to two parts A and B. Okay, so I can ignore this one for now. And assuming that the RAM itself is a square, what is the size of each decoder and how many AND gates is required for addressing an address? So overall, I want to first calculate my area. So that's 2 to the 32 is 2 to the 5th, and times 2 to the 10th by 8, 2 to the 3rd. So the total area is 2 to the 18th. So this is my area, essentially. And so I'm going to want 2 to the 9 address, 2 to the 9 basically on each side. So square root of this is 2 to the 9th. So my row decoder is going to be 9 to 2 to the 9. So that's how many addresses that's taking care of that. And since I only have 15 address lines, 15 minus 9, so this is 2 to the 15th divided by 2 to the 9, which is equal to this is going to be 2 to the 6. So this is going to be 6 to 2 to the 6th is my column decoder, and the number of AND gates is, well, here I'm just going to work with the assumption that I'm going to have 2 to the 9th AND gates here and 2 to the 6th AND gates here. And so 2 to the 9th plus 2 to the 6th. Yeah, I think that's right. I could technically, if I want to do this 2 input AND gates, which might be a little bit easier, so if I'm doing this 2 input, this is going to be 9 times 2 to the 9, right? And then 6 times 2 to the 6. And you don't need to calculate that out. So now let's determine the row and column selection lines that are enabled when the input address is the binary equivalent of 6A3C. So we've got 0, 1, 1, 0. A is 1, 0, 1, 0. 3 is 0, 0, 1, 1. And C is 1, 1, 0, 0. And so the first 9 bits, well, first I need to make sure I only have 15 select lines. I only have 15 address lines, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. I can ignore this one. And then, so this will be 1, 2, 3, 4, 5, 6, 7, 8, 9. So this is the first 9. And then this is the finals. 1, 2, 3, 4, 5, 6, 7, 8, 9. And then these will be my 6. And so my row select is equal to 0, 0, 0, 1, da, 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 1, 2, 3, 4, da, da, da. So it's going to be 1, A, 8, base 16. And column select is going to equal 3, C, base 16. And finally, for part C, this question is unrelated to parts A and B. Assume that the largest decoder that can be used in an M by 1 RAM chip has 13 address inputs, and that two-dimensional decoding is employed. So that means we can have 13 by 13, so we can have up to 2 to the 26 address lines. In order to construct RAM chips that contain more than M 1-bit words. Multiple RAM cell arrays with decoders and read-write circuits are included in the chip. With the decoder restrictions given, how many RAM cells arrays are required to construct a 256 megabyte by 1 RAM chip? So I have biggest RAM we can create equals 2 to the 13th times 2 to the 13th address lines, which is equal to 2 to the 26th. We want to implement a 256 meg by 1. So this is going to equal 2 to the 8th times 2 to the 20th, which is 2 to the 28th. And so 2 to the 28th divided by 2 to the 26th, because basically I'm going to use, this is the biggest RAM I can create. I'm going to make these out of this. I'm going to need 4 cell arrays. And that completes problem 5.